Hi everyone, my name is Lydia and this is what I wish they taught me about econometrics and introduction. In this video, we're going to talk about the first condition for what makes a good instrumental variable, and that is the relevance condition. The question is simple. Does the instrument actually affect the x? Because remember, we were trying to come up with the variable z that was capturing that clean variation in your x. So if you come up with a variable, you have to be able to understand whether does this variable affect the x as well, all right? And at the same time, I'm gonna flag this one up before we move on to the rest, is that this is the one condition that you can test directly. Okay, with the data. Which makes it both easier of a condition to verify and the one that researchers sometimes focus on too much. Let's keep the same exercise or example that we've been using in the previous videos. We're assuming that X is education. We're assuming that Z is our distance from uni, while Y is income. For distance to work as an instrument, people who live closer must actually obtain more education. Okay, so if distance has no effect on education, if people choose how much to study regardless of how far they live from a university, then distance basically tells us nothing useful about education. So it creates no clean variation, and that would make it a worthless instrument. To test relevance, we need what we call a first stage regression. In a first stage regression, what we do is we take our x variable and we run a regression of it on z, the instrumental variable. So this is x equals to some, let's say, pi 0 plus pi 1, z plus an error term, epsilon, okay? We are regressing x, which is our endogenous variable, on the z, which is our instrumental variable. Keep in mind, we're not using y in here, just x on z, because we're trying to figure out if there is some clean variation in x that can be explained by z. The name first stage, and you'll see the big picture in a few other videos, comes from the fact that the instrumental variable, or more largely the what we will call the 2SLS method, has two stages. This is stage one before we ever touch the y. We'll see the full two-stage procedure in a later video. But what are we looking for in this first stage regression? We're looking at this coefficient pi 1 in here. So through an OLS, we are going to estimate pi 1 hat, okay? And what we're doing is basically doing a test on whether this pi 1 is actually 0 or not. If pi 1 is 0, it means that z is not moving x. No movement in x, no clean variation, no instrument. And if this pi 1 is actually different from 0, that means that we'll have a test basically that rejects this null hypothesis. And it also means that z shifts x and the instrument is relevant, okay? So relevance is entirely about this pi 1. If this first stage is that, everything else will fail. So think of these as like the first hurdle you have to pass in order for you to be able to continue with an IV estimation, okay? So if this stage fails, everything else fails about the IV. The relevance condition, if you were to be asked in an actual exam, what are the conditions, and you're writing the first condition and you're saying it's the relevance condition, the mathematical way to write it, and you can choose whichever of the two to use in your exam, though personally I always suggest use both the name relevance and the actual math version of it. The math is the covariance between Z and X is different from 0. Okay, so the instrument must be correlated with the endogenous variable. So Z must actually change X. And again, this is the only IV condition that is directly testable with data. You simply run the first stage regression, check whether the pi1 is statistically significant and economically significant. A useful contrast that we can make is comparing two candidate instruments for education. So far we've looked at the distance to university. We know that people living closer, they get more education, quite relevant. Think of another instrument candidate. And let's say that is birth month. In fact, there is no systematic relationship with years of schooling. It's not like people who are born in February are more inclined to continue their studies, or people who are born in August and September are more inclined to continue their studies, okay? So in this particular case, the covariance between Z and X would be 0, which means that this is irrelevant, okay? The thing is, statistical significance, however, is not enough, okay? In practice, you check pi1 in the first stage regression, but statistical significance alone is not enough. A coefficient can be statistically significant, but economically tiny. So if pi1, let's say, is very small, even if it's not 0, but it's very small, the instrument barely moves X. So that creates what we call a weak instrument. So a weak instrument doesn't come only because you have established the relevance condition. If economically it doesn't create that variation as well that we want, or enough of that variation, it's also useless. This is also one of the reasons we need usually stronger diagnostics than a simple t-test. And the diagnostic in the first stage would be sometimes also an F statistic, because suppose your instrument changes education by only 0.001 years on average, okay? Do you think that would be useful in your study? Your answer should be probably not, right? So what do you need to do to make sure, like, okay, I have established that the distance is statistically significant. How do I make sure that it's also economically significant? Okay. For the first stage, you can use an F statistic, or like the standard diagnostic test that you use like for regressions. And you can use the usual rule of thumb, where if F is bigger than 10, then the instrument is sufficiently strong. And if F is smaller than 10, there is concern about weak instruments, okay? So the F statistic test, whether the instrument or instruments jointly explain a meaningful amount of variation in X, would be your next step. A single t-test is not enough when you have multiple instruments as well. So the F statistic would handle that joint test as well. And the F bigger than 10 rule comes from the paper of Steiger and Stock, 97. It's quite a landmark paper on weak instruments. That's why it's also used. Now, why weak instruments are dangerous? A weak instrument barely moves X, so the clean variation we're trying to isolate is tiny. So the consequences would be that the IV estimates become imprecise. So you're very likely going to have huge standard errors. So imprecision. The IVs can be severely biased. Okay, so in the direction of the OLS, which we are trying to move away from. And ultimately, confidence intervals also become unreliable. So a weak instrument doesn't just give you a noisy estimate, it can give you a biased one, which entirely defeats the purpose of using the IV. So relevance condition, once again, requires covariance Zx to be different from 0, verified by a strong first stage F statistic, ensuring the instrument provides enough variation in X to identify the causal effect. In the next video, we'll study the second condition. It's a little bit harder, and I like relevance. It cannot be tested directly. So stay tuned, and I'll see you in the next video.